So the mean value theorem for derivatives, it's pretty straightforward. Mean value theorem for derivatives says that if you have a function that's continuous on a closed interval and that it's also differentiable, so you can take the derivative at every point on the open interval from a to b, then there is at least one point between a and b where the instantaneous rate of change, or where the derivative, is equal to the average rate of change, or the slope between the two inputs, right? Or in more algebraic terms, there's one place, C, where f prime of C is equal to f of b minus f of a over b minus a, right? Where there's the average rate of change is equal to the instantaneous rate of change at some point. That's the mean value theorem for derivatives. Couple of points to note when you are verifying the mean value theorem or looking for values: make sure that you state that it's continuous and differentiable, and make sure you give a reason why both those things are true. Okay. So we're going to just do a nice, simple, easy one. We got x squared. We want to show that this function satisfies the hypotheses of the mean value theorem, and then find the solution to where it occurs. So first off, is f continuous on 0 to 2? And if so, why?
Polynomial.
Yes, it's continuous because it's a polynomial. And we can also use that that reasoning for the derivative also, right? Polynomials are always differentiable for their entire domain. So yes, it satisfies both hypotheses of the mean value theorem, that it's continuous on the closed interval and that it is differentiable on the open interval from 0 to 2. So now all we care about is f prime of c. Well, what's f prime? F prime is 2x, right? And so if we evaluate that at c, that ought to be 2c is equal to f of 2 minus f of 0 over 2 minus 0. Or 2c is equal to, what's f of 2?
4.
So we got 4 minus 0 over 2. 2c is 2, or c is 1. So the place on that interval where the average rate of change is equal to the instantaneous rate of change is at x equals 1 or c equals 1. Easy enough?
Yeah.
All right, good. Then there is the basic corollary to the mean value theorem, which is called Rolle's theorem. Rolle's theorem has the same hypotheses to start with, but then adds in that f of a equals f of b. So if the function is continuous and differentiable on that interval, and the y values of the starting point and the ending point are the same, then somewhere in between there, I must have had a place where the derivative was equal to 0, right? There might have been more than one place, but there's at least one place. There's no way to draw a line connecting between there, or a curve connecting between there, where the derivative isn't equal to 0 at least one place. Even if I tried to draw, let's say, horizontal line through there. Oh, that was supposed to be horizontal. That was supposed to be horizontal. Right, if the derivative is equal to 0 at at least one place on that interval, it's equal to 0 at every place on there. The only way we could draw it between there, where this didn't have a place where the derivative equaled 0, would be something like this, where there's a sharp corner, but then it's no longer differentiable on the interval. Or if I were to do it like a cusp or something, it's still not differentiable at that point, which means it's not differentiable on the interval, which means we didn't satisfy the hypotheses of that mean value here. Good or no?
Great.
Great. All right. So sometimes they will ask you something about Rolle's theorem on the AP test. Let's just do one real quick here. first off, does this satisfy all of the hypotheses of the of Rolle's theorem on this interval from 1 to 4? So is f continuous on 1 to 4? Yes. And f prime exists on 1 to 4 because it's a polynomial. And then f of 1 equals what?
13.
13. And what's f of 4? Should also be 13. So this tells us that f prime of c equals 0 somewhere on the interval from 1 to 4. And we should be able to figure out where that exists or where that happens. That'd be 8c minus 20 equals 0, right? The derivative is just set to 0. C is 28, or if we divide that by 4, 5 halves. Good or no?
Splendid.
Great. All right. Thought I deleted this page, but apparently I didn't. Now I did. All right. Now we're going to talk about increasing, decreasing stuff. And I'm going to go on a rant about the College Board for a second, as I always do. But we're talking about increasing and decreasing functions. So if we have a function that is continuous on the closed interval a to b and differentiable in the open interval from a to b, if the derivative is positive, the function increases on the interval. And if the derivative is negative, the function decreases on the interval. And we'll note that whenever we talk about increasing and decreasing intervals, you have to use brackets. Even though that's stupid, the College Board wants you to indicate increasing and decreasing intervals with brackets. Okay. So derivative is positive, function increases. Derivative is negative, function decreases. Everybody good with that? Great. Okay. If our derivative changes signs from positive to negative, that would indicate that the function goes from increasing to decreasing. Tells us that we have a local maximum. If it goes from negative to positive, should be a local minimum, like decreasing to increasing. And if f doesn't change signs at some value, then there's no local extrema there. We're specifically talking about at a critical point, and we remember what is a critical point. Critical point is a place where f prime equals 0 or where f prime is undefined. So f prime is 0 or f prime is undefined is a critical point. And if at that critical point, we go from positive to negative, we get a max, negative to positive, we get a min. No sign change, no extrema. You always have to show that there is a sign change to indicate whether there's a max or a min. You can't just say that it's a max or a min without proving it in some way, usually with a sign chart. And then endpoints, our endpoints, that endpoint is a local min. That endpoint is a local max, right? And same applies for over here on the right-hand side. Right? That's a local max, and that's a local min. Easy enough?
Yeah.
Great. All right. Now, concavity. Concavity can be indicated using the second derivative. So whenever our second derivative is positive, we are concave up. And whenever our second derivative is negative, we are concave down. And just to refresh your memories, concave up, concave down, right? The reason this is true is because if the second derivative is positive, that's telling us that the first derivative is increasing, right? And if our first derivative is increasing, that means that the slopes of the tangent lines are getting larger. And I can only be concave up if those slopes of the tangent lines are getting larger, right? If I suppose I started over here, these are negative, very steep negatives, and then less steep negatives, and then less steep negatives, and then zero, and then not very steep positives, and then steeper positives, right? The derivatives, the slopes of the tangent lines are getting larger, they're increasing, it's concave up. And the same goes for this concave down value. Good or no?
So good.
Great. Points of inflection are places where our function changes concavity. It has to have a tangent line there, which means that the derivative has to exist at that point. Or sorry, the function has to exist at that point, not the derivative. The function has to exist at that point, and there has to be a change in concavity, as in the sign of the second derivative has to go from either positive to negative or negative to positive. Everybody good with concavity? Great. All right. We also have the second derivative test for local maxima and minima. If at a place where the first derivative is 0, and this only works if the first derivative is 0 at that c value or that x value, and the second derivative is negative, it gives us a max. If the second derivative is positive at that value, it gives us a min. So remember, the derivative being 0 tells us that it's going to either have a local max or a min, most likely. If the second derivative is negative, that tells us concave down. And a concave down function can only have a maximum there at that place where the derivative is 0. And if it's concave up, it can only have a minimum at that place where the derivative is 0. Okay? This is the second derivative test, and this is a good one that you should know. It can be really helpful, especially if plugging in values of a sign chart to prove that it's a minimum or a maximum is really difficult. But keep in mind that this does not work in two cases. One, where the second derivative is 0 or does not exist there. And also, it does not work if f prime is undefined. It only works if f prime is 0 at that value. Good or no?
Good.
All right. So let's take a nice simple function and let's see. I think you guys should, with any luck, be able to do all of this on your own. What do you guys think?
Yeah.
All right, so I'm going to give you 2 or 3 minutes to try and work through that. And then we'll come back and make sure that you got it all perfectly done. So increasing and decreasing local extrema, so local maxes, local mins, intervals of concavity, and any points of inflection that x cubed minus 12x minus 5 might have. Ready, go. So first off, our derivative, f prime, should be 3x squared minus 12. And we need to figure out when that equals 0 and when it's undefined. It's never undefined, but it equals 0 when x is what? Plus or minus
2.
So first off, we can, and we're going to do this both ways just for fun, we can make a sign chart to see if these are local locations of local maxes or local mins. The sign chart will also help us determine when the function's increasing and decreasing. So first off, we'll take something that is between -2 and 2, like 0, and plug it into our derivative. I indicate this as a sign chart for the derivative. So if I plug in something like 0, I get a negative, which tells me that my function is decreasing. Plug in something more than 2, like a million, and I get a positive, and it's increasing. And plug in something like -1 million, the squared makes it positive, and we're positive still over here. So we know that there's a local max at -2 and a local min at 2, and we're increasing from -infinity to -2 and 2 to infinity, but decreasing from -2 to 2. I'll write all that out in a minute once we're done with everything. Then the next thing we need is a second derivative. So f prime ought to be 6x, which is never undefined, but is equal to 0 when x is 0. So we'll make a sign chart with the second derivative with 0. And when it is a positive that we plug in, we get a positive, concave up. And when we put in a negative, we get a negative, which is making it concave down. Tells us that we do have a point of inflection. And in order to figure out what the actual point is for the point of inflection, we need to find f of 0. And we're also going to need to find f of 2. And we're also going to need to find f of -2. So f of 0 is the easiest one, probably. That one's just -5, right? And if we look at f of 2, what is that? 8 minus 24 minus 5, that ought to be negative, what is that, 21? Yeah. And then if we plug in -2, that ought to be -8 plus 24, which is 16, minus the 5, which is 11. So if we wanted to write all of this out, our function is increasing from -infinity to -2, union 2 to infinity, and it is decreasing from, gotta write brackets here, -2 to 2. I disagree about the brackets, but the College Board wants it to be brackets, so you gotta do brackets. And then it is concave up, and that's from 0 to infinity. College Board gets it right on that unless you use parentheses. Concave down from -infinity to 0. And then we have a local max of 11. And it doesn't ask where it occurs, but we'll say at x equals -2. We have a local min of -21 at x equals 2. And we have a point of inflection, 0, -5. Everybody good with that? Is that what you all had?
I have a question.
Yeah.
For the concave up and concave down, why did you not use brackets?
Because the College Board does it correctly for those. It should be parentheses because you can't be concave up or concave down at a point of inflection. So concave up intervals will always be in parentheses, concave down intervals always in parentheses, no matter what. The increasing, decreasing are the ones you have to use brackets on the endpoints, as long as the endpoints aren't infinity, because that's not really an endpoint. I disagree with the College Board saying these should be brackets. I think these should be parentheses also, but because you're not increasing or decreasing when you're up here at -2. What is it? -211. You're not increasing or decreasing at that point. At that point, you are transitioning between the two. All right. So answer your question? Good?
Yes.
Cool. All right. We're going to add a little bit of stuff into this one. For this one, we're going to look for horizontal asymptotes as well. So I'd like you guys just to practice this and do this one on your own also. So I'll give you about 2 or 3 minutes here, maybe 4 minutes. This one's a little bit more difficult. Don't worry about approximating out the values, just use values of E when you're plugging stuff in if you need to. So all that same stuff plus asymptotes. Ready, go. So first off, let's talk about horizontal asymptotes, because that we can do without the derivative. The limit as x approaches infinity of f of x. What's that limit? That's just an infinity times another infinity, which would be infinity. So no horizontal asymptote to the right. What about the limit as x approaches negative infinity of f of x? Then we have an x squared over an e to the x, because that'll drop to the denominator, right, if it becomes a negative infinity. And the e to the x will increase more rapidly than the x squared, so this should be 0. So we've got no horizontal asymptote to the right, and we have y equals 0 to the left. Everybody good with that?
Yeah.
All right. Next one. For when is this increasing and decreasing in the local extrema? We'll need a derivative. So f prime, that's a product rule problem, right? So x squared minus 3 times the derivative of e to the x, which is e to the x, plus 2x times e to the x. And we can factor out the e to the x from all of that. And we can factor that into what, e to the x times x plus 3, x minus 1, which we know will never be undefined, but we can figure out that it equals 0 when x is negative 3 and when x is 1. And making a sign chart, plug in something like 0. That's going to give us a positive times a negative, so negative will be decreasing. Plug in something like 1,000, that's going to be positive, 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 so it'll be increasing when you multiply those together. And plug in something small like negative 1,000. The e to the negative 1,000, this is going to be positive still, but these will both be negatives, so that'll still be a positive overall. And we'll need to figure out what is f of negative 3 and what is f of 1. And f of negative 3 ought to be 6 over e cubed. And f of 1 looks like ought to be negative 2e. So we have a local max of 6 over e cubed at x equals negative 3. And we have a local min of negative 2e at x equals 1. We are increasing from negative infinity to negative 3 and from 1 to infinity. And we are decreasing from negative 3 to 1. Everybody good with all of that?
Yep.
All right. And then our second derivative will tell us about the concavity. And that's the derivative of this, right? So that ought to be e to the x times the derivative of the, what was it, x squared plus 2x minus 3. So 2x plus 2. And then plus e to the x times the x squared plus 2x minus 3. And once again, we can factor out the e to the x, leaving us with x squared plus 4x minus 1. And that's never going to be undefined, but it will equal 0 whenever x squared plus 4x minus 1 equals 0. which I guess we could just complete the square with that. X squared plus 4x equals 1. We're going to have to add a 4 to both sides. This will factor to x plus 2 squared, and that'll be 5. And we got x plus 2 equals plus or minus root 5, or x equals negative 2 plus or minus root 5. Good or no?
Good.
Great. And put those values on a sign chart and plug something in the middle in. What's between negative 2 minus root 5 and negative 2 plus root 5?
0.
-2.
Yeah, 0 is, yeah. Negative 2 is, that's true. 0 also is. Either one will work. Be careful just by picking 0, though. Right? If this is negative 2 minus root 3 and negative 2 plus root 3, 0 is not between those, right? We know that negative 2 plus root 5 is more than 0, though, because the root 5 is more than 2. So just be careful with that. If you plug in 0, though, you get a negative in there, which means you're concave down. Plug in something greater than this, like a million, and you're going to get a positive and a positive. Concave up. And plug in something like negative a million, you're going to get a positive, and then this will equal out to be a positive also. So you're going to be concave up. So we could say that we are concave up from negative infinity to negative 2 minus root 5, union negative 2 plus root 5 to infinity. And concave down on the rest. And then, did I ask for points of inflection? I did. That was a mistake. Clearly, I shouldn't have done that. So, x squared minus 3 times e to the x. Well, that's kind of a pain. But, yeah, I don't know. I don't want to figure out what those are. So, our points of inflection are negative 2 minus root 5 f of negative 2 minus root 5 and negative 2 plus root 5 f of negative 2 plus root 5. You could figure out what those are if you really are desperate to know, but concept-wise, it doesn't really matter. You can plug those into the original function and figure it out. Any questions or issues with that? All right, so just a couple of quick things to remember. First off, that the second derivative being 0 does not necessarily make it an inflection point or a point of inflection. You can have the second derivative equaling 0 at a point that is not an inflection point. So if we look at this one, f prime before x cubed and f double prime would be 12x squared. Well, that equals 0 at x equals 0. But if you do a sign chart with the second derivative, putting in a positive gives you a positive, and putting in a negative also gives you a positive. There's no sign change. So make sure you check. Okay? And also remember that you have to check when the second derivative is undefined or when the second derivative doesn't exist, not just when the second derivative is 0 for inflection points. So here we have f prime is 1/3 x to the negative 2/3, and f double prime is negative 2/9 x to the negative 5/3. This never equals 0, but it's undefined at x equals 0. And so if you plug in a positive, you end up with a negative. And if you plug in a negative, this denominator becomes negative. And so you end up with a positive. And so you do have a sign change. So make sure you confirm that there's a sign change and make sure you check for when the second derivative is undefined for points of inflection also. Okay. Remember that a it could be undefined because it's a vertical tangent line there on the function, but it might still be a point of inflection going, we're used to them looking like this, but they can also be turned horizontally as well, so that we have a vertical tangent line at the inflection point. Good or no?
Good.
All right. Okay. So here we've got a particle that's moving along the x-axis, and we're giving it a position function here of 2t cubed minus 14t squared plus 22t minus 5. Let's describe the motion of the particle in terms of velocity and its acceleration by using the first and second derivative tests. So first off, what's the velocity function?
6t plus 28t plus 22.
6t squared minus 28t plus 22. Good. Okay. Never going to be undefined, but we'll look when it's 0. Okay. If we want to divide out a 3 from that, what does that become? 3t squared minus 14t plus 11. Let's hope I picked something that factors nicely. Did I?
It's not
Like I
divisible
did.
by 3.
What's
That's
that?
a 22.
I don't know what you just said.
There's a 22, and that's not divisible by 3, right?
22 is
Wait,
not
hold
divisible
on,
by
never mind.
3, but I divided everything by 2, not 3.
Yeah, I forgot.
Yeah. All right, so that gives us t equals 11 thirds and t equals 1. And if we make a sign chart with those, there's 1, there's 11 thirds, and we might want to stop this over here at 0 because we're not going to have t values less than 0. So let's make sure we only plug in things between 0 and 1, between 1 and 11 thirds, and greater than 11 thirds. This is velocity. So plugging in something like a half is going to give you a negative times a negative, which is going to be a positive. Plug in something between 1 and 11 thirds, like 2, it's going to give you a negative and a positive, so your velocity is negative. And then plugging in something greater than 11 thirds, like a million, is going to give you 2 positives, and we're going to have a positive velocity. So we could say that it is moving to the right from t equals 0 to t equals 1, and t equals 11 thirds to infinity. And we could say it's moving left from t equals 1 to t equals 11 thirds. Good or no?
Why didn't you use the brackets for this?
Say that again?
Why didn't you use the brackets for those?
Oh, we could have.
Oh, okay.
Yeah. And I've noticed that with the velocity problems, they seem to accept either brackets or parentheses on those. But that makes me a little nervous. I know that if you write it out in words, they will definitely accept it. But they never make it, any sort of distinction for velocity functions, whether you're talking about moving right or moving left, whether it should be brackets or parentheses. But I've seen in like student work examples that they've given points for both, so should be okay either way. What about our acceleration function? Should be 12t minus 28. Set that equal to 0. Ought to give us t equals 28 twelfths or 7 thirds. So put in something like 1, and you're going to get a negative. So the acceleration is negative, which means that it is slowing down. And greater than 7/3, like 1,000, this is positive, and it is speeding up. So we'll say that it is decelerating from t equals 0 to t equals 7/3, and it is accelerating from t equals 7/3 to infinity.
Since its motion is to the left from 1 to 11/3, wouldn't it be more accurate to say that it's accelerating to the left from t equals 0 to t equals 7/3? Because it's accelerating from 1 to 7/3. It's just accelerating to the left.
I mean, the acceleration means that your velocity is increasing, and decelerating means that your velocity is decreasing. So technically, no, what you're saying is wrong. I'm moving to the right, but I'm slowing down from t equals 0 to t equals 1. I'm decelerating because my velocity is getting smaller. And even between t equals 1 and t equals 11/3, well, sorry, t equals 1 to t equals 7/3, when I'm moving to the left and still decelerating, right, I'm still getting smaller. I still have a negative velocity, and that is getting to be a larger negative number. I'm still decelerating.
Okay.
And then from 7/3 to 11/3, from 7/3 to 11/3, you're still moving to the left, but you're moving to the left less quickly. So you are accelerating, your actual velocity is increasing again. And then eventually at 11/3, you start moving to the right again. And then, does that make sense?
Yes.
Okay. Any other questions on that? Okay, one other thing to note here is that if sometimes we talk about, hold on a second, sorry. Sorry about that. We talk about when, and this I think might be what you're sort of getting at here, is that if velocity and acceleration have the same sign, then the speed is increasing. And if velocity and acceleration have opposite signs, then the speed is decreasing. But that's specifically speed, right? Not velocity. Speed is the absolute value of the velocity. So based on speed, what you're saying is correct, no, but based on velocity and acceleration, it's not.
Yeah,
that makes sense?
Could you say accelerating to the left instead of decelerating? It would still be accurate, right?
I guess, yeah. I mean, I wouldn't use that terminology ever if it were me.
Okay.
But if you want to,
I'll stick
sure.
to decelerating.
All right. All right, let's see if we can get in here and graph a couple of functions, and then we're going to be done for the day. So in order to graph this function, we're going to need to find all that stuff using the first and the second derivative tests. And maybe finding x and y intercepts also might be helpful. So when does this equal 0? Let's find some x intercepts. Factor out an x cubed and see that this has x-intercepts at x equals 0 and x equals 2. Yeah? Yeah.
Absolutely.
All right, what about the derivative then? 4x cubed minus 6x squared. 2x squared will leave me with a 2x minus a 3 there. And tell me that I have potential local maxima or minima at 0 and 3/2. So I'll make a sign chart. Oh, well, I can't make that look all right over there. So if I plug in something between 0 and 3/2, like 1, I'm going to get a positive and a negative. So I'm decreasing. And if I plug in something greater than 3/2, like 1,000, I'm going to get a positive and a positive. So I'm increasing. And a negative number is going to give me a positive and a positive and a negative. So we're going to still be decreasing there. Everybody good with that?
For sure.
Okay. So an important value we might need is then f of 3/2. So let's find f of 3/2. What is f of 3/2? That's 3/2 to the 4th, which is what, 81/16 minus what? Minus 27 over 4. Yeah. Which if I get a common denominator, that's going to be 20. What is that going to be? Ought to be 27 over 16, negative 27 over 16. Everybody agree with that?
Yeah.
Oh, good. Somewhere right around there, a little bit above negative 1.5. And then we'll find a second derivative, which ought to be 12x squared minus 12x. Set that equal to 0, take out the 12x. And we got 0 and 1 for potential points of inflection. Plug in something more than 0 but less than 1, like a half, and I get a positive and a negative. And plug in something more than 1, like a million, and I get 2 positives. And plug in 2 negatives, negative, and I get 2 negatives, which is concave up. So the important point here ought to be f of 1. What's f of 1? Looks like negative 1. And it would appear that I have a function that is decreasing all the way from negative infinity to 3/2, but it changes in concavity from concave up to concave down at 0. Then changes again in concavity from concave down to concave up from 1 to 3/2. Stays concave up, but begins to increase after that. And we get some function that looks about like that. My little concave down section there is a little shaky, but it's supposed to be concave down. Good or no?
Beautiful.
Great. Let's do one more of these and then we'll call it good for today. Hopefully we can get through this one in the next 10 minutes. First off, let's find some intercepts. Set this equal to 0. That's going to give us intercepts of x equals 0, right? And then 3 minus 2 cube roots of x equals 0, or cube root of x is 3/2, or x equals 27/8. Good or no?
Good.
All right, so each of those is 1 there. 27/8 got to be what, a little more than 3, right? Yeah. Then we'll go in and take a derivative. Might be easier to take the derivative if we distribute everything first. So let's call this f of x equals 3x to the 2/3 minus 2x to the 1/3 times x to the 2/3 is just minus 2x, right? So our derivative then ought to be what? 2x to the negative 1/3 minus 2. And now we'll need to figure out when that equals 0 and when that's undefined. So that's 2 over the cube root of x minus 2. And we'll get a common denominator. And gives us 2 minus 2 cube roots of x over the cube root of x. And we'll say this is undefined at x equals 0. And it equals 0 if 2 equals 2 cube roots of x, or x equals what? 1. Good. All right, so we're going to need the value at f of 1 to plot that point eventually. So f of 1 ought to be 1 times 3 minus 2. F of 1 is just 1. And let's make a sign chart here with 1 and with 0 on it. Plug in something less than 0, plug in a negative. Well, the cube root of a negative is a negative, right? And whatever negative I put in here, I'm going to get another negative here. 2 minus a negative is going to be a positive. So my numerator is going to be positive, but my denominator is going to be negative. So we're going to decrease. And then between 0 and 1, like a half, this bottom will be positive. And the cube root of a half is less than 1. So when I multiply it by 2, this value is going to be less than 2. So when I subtract, I'll get a positive. So it should be increasing. And if we plug in something more than 1, like a million, I'm going to get a positive in the denominator, but a negative in the numerator, and it will be decreasing. So far, good?
Yeah.
All right. Now what about f double prime? F double prime, I'll just use this to take its derivative. Ought to be negative 2/3 x to the negative 4/3, right? Anything make that 0? Nope. But it is undefined if x equals 0. Well, we've already got that point. So let's just make the sign chart using 0. Plug in something more than 0. If I plug in a positive, this comes out to be a negative. And if I plug in a negative number, I'm going to raise it to a power of 4, which is going to make it positive. It's going to stay positive when I cube root it, and it's going to become negative when I multiply it by the negative 2/3. So no change in concavity at x equals 0. So we have a function that decreases, but is concave down to this point. Then it increases, but is still concave down. Then it decreases, but is still concave down. So we have a function that looks about like that. And we should have been able to be clued in that at x equals 0, we were going to have a cusp there because we knew that the derivative was undefined. So it wasn't going to be a nice smooth local minimum there. It was going to be a local minimum that came from a cusp. Everybody good there or no? Feel like we have a pretty good idea about how to do this?
Yes.
Spectacular. That's it for today. We're going to stop.